Hey boy.
In this episode, we will be discussing about chemical kinetics, specifically the rate-law equation and the method of initial rates. First, let us define what is chemical kinetics. Chemical kinetics is the study of rates of chemical reactions, the factors that affect reaction rates, and the mechanisms by which reaction occurs. Now, are you familiar with this equation? We have two questions in mind from the equation shown. What does K stand for? What is A and B? This is the rate-law equation. This is the central concept of chemical kinetics, which is solely based on experiments. Well, what exactly is this? Remember that in a chemical reaction, there are always reactants on the left side and products on the right side. The rate law depends on the reactant concentrations and the temperature. This equation relates the concentrations of chemical reactants to the reaction speed or rate, wherein R is the rate variable, K is a proportionality constant or the rate constant specific for any given reaction at a given temperature, A and B are the concentrations of the reactant compounds, and X and Y are the reaction orders. The values of the exponents x and y and of the rate constant k bear no necessary relationship to the coefficients in the balanced chemical equation for the overall reaction and must be determined experimentally. They define how the rate is affected by the given reactant concentrations. Remember, all these components must be obtained by the process of the execution of an experiment. The components of a rate law are found starting by measuring the initial concentrations for determining the initial rates. These initial rates will be used to determine the reaction orders, and using these values, the value of the rate constant will be calculated. Using the rate law equation, the rate for any given initial concentrations can be predicted. Determining the initial rates are crucial in this topic. There are three common approaches in determining the initial rates. Firstly, spectrometric methods are used to measure the concentrations of a component that absorbs or emits characteristic wavelengths of light. For example, in the given chemical reaction, only NO2 has a color which is brown, an indication that it absorbs some wavelength of the visible light. Known amounts of the reactants are injected into a tube of known volume within a spectrometer, which is set to measure the wavelength and intensity of the color. Another approach is using conductometric method. This method relies on the change in electrical conductivity of the reaction solution when non-ionic reactants form ionic products or vice versa. For example, the substitution reaction between a haloalkane, such as 2-bromo, 2-methylpropane, and water. The HBr that forms is a strong acid, so it dissociates completely in water. As time passes, more ions form, so the conductivity of the reaction increases. The last method is called manometric methods. This method requires employing a manometer attached to a reaction vessel of fixed volume and temperature. The manometer is responsible for measuring the change in pressure in the reaction vessel due to a reaction that involves a change in the number of moles of gas. A good example is the decomposition of hydrogen peroxide. The rate is directly proportional to the increase in pressure as O2 gas forms. We can use the method of initial rates to deduce the rate law from experimentally measured rate data. Usually, we know the concentrations of all reactants at the start of the reaction. We can then measure the initial rate of the reaction corresponding to these initial concentrations. The following tabulated data refer to the hypothetical reaction at a specific temperature. Using the data, let us determine the order of the reactions with respect to both O2 and NO, determine the rate law equation, and determine the overall order of the reaction. Let's start by writing the rate law. We see that the initial concentration of NO is the same in experiments 1 and 2. For these trials, any change in reaction rate would be due to different initial concentrations of O2. Now, let us compare experiments 1 and 2 by substituting their values to the equation. Then we cancel same values from the numerator and denominator. We then divide both sides of the equation and isolate x to get the order of reaction with respect to O2, which is 1 or in first order. We then do the same process in computing for the order of the reaction with respect to NO, but this time we use experiments 1 and 3 as O2 has the same initial concentrations for both experiments. The computed order reaction is second with respect to NO. To get the rate law equation, we simply substitute the compounds to the given formula, A being O2, X being 1, B being NO, and Y being 2. There we have our rate law equation for the reaction. Now, for the overall order of the reaction, we just add the computed orders of the reaction. With this being said, the overall order of the reaction is 3 or in third order.
Let's kill this love. Yeah.